So again, so what I'm going to do is we started introduction to convolutional neural network, and we already went through the fundamental operation, how the convolution layers are formed. So I mean, I will quickly go over like those slides today as well, just to keep you in touch as we proceed in this lecture. Okay. So what we're going to do is we are going to first go through this fundamental operation and then talk about like other aspects of convolutional neural networks. So as we discussed, the core building block of a convolutional neural network is a convolution operation or a correlation operation. And the idea is we try to preserve the spatial structure of your input. And as we process your data in this network, we go from volume to volume. And to be able to move from volume to volume, we have to perform this transformation using the filtering operation, for which we use these filters. Okay, so this is just showing one filter, which is actually applied at all the possible locations of this input. And for each location, we are going to get like one response. So we collect response from all the locations to get an activation map. And of course, we have like multiple such kernels. And that's how we go from volume to volume. Okay, so and these kernels actually these kernels actually form a layer inside your convolutional neural network. Right, so once you have this convolution layer, which is nothing but like a set of kernels, and the only parameters are how many kernels you are going to use and what is the shape of these kernels. And then again, using these kernels, you apply a filtering operation on the input and you get the output activation map. And this constitutes like a one layer of your CNN. You can actually stack multiple such layers on top of each other. And again, you are going from volume to volume. So you start from the image, which is again considered as a volume. And depending upon like how many filters you have, what is the shape of those filters, you will have certain shape of these activation maps. And we talked about like how the third dimension of these filters should match the depth of the input volume here. In this case, it's input image, which has 3 channels for R, G, and B. So therefore, we have to match this depth with the third dimension of the kernel. So we don't define that. We only define the first 2 axes for these filters. So that's one point. The second point was the thickness of these activation maps is determined by how many filters you are using in this particular layer. Okay, so for example, in this case, if we are using 6 different filters, the depth is going to be 6, because for each filter we are going to like get a flattened feature map. Okay, so those are the 2 important point which should be noted here. And the dimensions, like why we move from 30 to 28, what is the role of like what kind of filters we are using, we are going to cover that later. And then you can see like so one interesting thing I think which we didn't cover last time was, so it's fine, I mean the depth should actually match. So when you're matching the depth, what's happening is when you're placing this kernel at any location, then in the spatial region, you are actually covering 5 cross 5, which means like the 25 pixels which are in the neighborhood, right? But in the depth aspect, you are actually covering all the pixel values, okay, at once. So you are spanning across spatial dimension like X and Y, but you're not spanning across depth. So you're considering all those values just like a single time, right? So all the values are considered when you compute the linear combination of all the activation maps. Okay, so that's one thing to note here. So, all right, so I think this part until this point we covered last time. Now, let's talk about when we say, okay, a convolutional neural network has like certain number of parameters, what exactly that means. And this we have already seen in neural networks, where we saw that like the arrows which are actually going from input to output neuron. So those weights are the parameters, and those parameters are learned. So let's try to understand what are parameters in these convolutional neural networks. Let's say we have a certain volume. You can say like it could be input image or it could be a feature map in between your CNN. Okay, so the shape is 32 cross 32, depth is 3. And let's say we are using a filter of shape 3 cross 3 cross 3. As we discussed, if you apply this at one location, it's going to give you one number. And then you convolve over all these spatial possible locations, it's going to give you activation feature map. All right. Now, this blue block over here, these are activation values. Like it's kind of a response of your network on whatever features were coming in from the previous layer. All right. And if it's an input layer, if it's an image, then these are just pixel values. Okay, so these are data points, which means these values will change with like different samples. And these are not parameters. Okay, so these values are not defined by the network. It is property of the data. Again, these activation maps, these are not parameters. This is kind of a data flowing in your network. So these values will depend upon what kind of features were present in the previous layer. All right, so these are not learned. These are just like showing how your data is flowing. So then what exactly are parameters which we are trying to learn? So these filters over here. Okay, so let's say if we just consider one filter, which is 3 cross 3 cross 3, which means this filter will have 27 different values. All right, so those 27 different values are actually used when you transform this input volume to the output volume. All right, so those values are actually parameters. They are independent of what input sample you will use. Okay, let's say you select like image number 1. This filter is not going to change. It will remain the same. The only values which will change is this blue block over here and this orange block over here. And if you pick another image, again, the values of blue block will change. The values of orange block will change. The values of this filter will not change. Okay, so then this filter is actually the parameter of your network. And this filter is defining how this activation map is actually transformed from like this stage to a different stage. Okay, so which means if we just consider one filter, we have 27 different parameters. And we were talking about like sharing of these parameters, and we are sharing because we are applying the same filter at all the possible locations. Okay, so that's what like parameter means in a convolutional neural network. So let's say you have this input image and you have a convolution layer, which is like some set of filters. And let's say we are using 6 different kernels or 6 different filters. So I will use like these terms interchangeably, kernels and filters. We have seen it means the same thing. So we are using 6 different kernels, and the shape of the kernel is 3 cross 3 cross 3. So that constitutes like this convolution layer. And if we use this convolution layer on this input data, we'll get something like this form of activation map. Now, if we have to say, okay, how many parameters we have in this particular convolution layer, we can just count these parameters. Okay, so this is going to give you 162, which means this convolution layer has 162 different parameters. Similarly, you can actually create, you can have more than 6 kernels. You can have as many as you want. And that will change the number of parameters you have. So one thing which will change the number of parameters is how many kernels you're using. The second thing which is going to change the number of parameter is what is the shape of your kernel. Okay. And then you can stack like these convolution layers on top of each other. And if you compute number of parameters for one layer, you can just add like for all the layers. And then you can say that, okay, this whole network actually has these many number of parameters. So now let's try to understand the convolution operation. I will give you like some more insights. What exactly is happening when we are performing this operation? Of course, we have seen filtering, like how it works and what this filtering actually means. So let's say we have a function ft, and you can see it's a simple step function, or you can say like a unit function. And from negative infinity, it's at 0. And as you come to this point, it directly jumps to 1 and stays there, and then comes down and again remains 0 as we go to plus infinity. So that's a simple function. Let's say we have a kernel, which is like almost have like similar kind of structure. And again, this kernel is like, if you go negative infinity, it's 0, goes to 1, comes to 0, and stays there. Okay, so in this case, this is the function, this is the kernel, and of course, these are like just one-dimensional functions in kernels. But whatever we are trying to discuss here, you can easily generalize that to two-dimensional or three-dimensional or any high-dimensional space. Now, if we convolve these two functions, treating this as kernel and this as function, now what exactly is happening? You know that when you convolve, you actually you flip your kernel, right? In this case, if you flip, it doesn't matter because it's kind of symmetric. It's just like your plus infinity will go to negative infinity and negative infinity will go to plus infinity. Okay, so that's one thing. Then what you do is you try to apply this kernel at all the possible locations for this function f. And those locations will start from negative infinity. Of course, I'm not showing negative infinity here. We are starting from -2. Of course, you can extend this to negative infinity. And on the positive side as well, you can go to plus infinity. So you start from this point, you take your kernel, and then you find the correlation. All right. So what you see, this kernel is actually not matching with the function at this location. Okay, so the response will be 0 because you know that it's just element-wise multiplication. In this case, it's just 1D function, and we just have two values, either 1 or 0. And at this location, if you apply the kernel gt has value of 1, but ft, the function, has value of 0. If we take element-wise multiplication, that's going to give you 0. All right, so it's 0. Now what you will do is you will stride your kernel towards right. Okay, and then you will keep computing that convolution value. So you keep moving towards right, and you can see like still it's 0, it's 0, it's 0. But as soon as you reach like this location, you're seeing like some kind of overlap between the kernel and the function. Because what's happening, if you look carefully, like this red region here, at this point, it's starting to overlap, and which is indicated by this yellow color here. Right, so the area of this yellow color actually shows how much overlap you have between function f and kernel t at this particular time step. Okay, so then you will see as you keep going towards right, the overlap is actually increasing, and at the center over here, they will perfectly match with each other, and you see you will get like a highest response. Okay, so this black plot over here, this is actually showing you the result of convolving kernel G with function T. Okay, so you can see like from the left, it's 0, it's increasing. At this point, there's a perfect match. Then again, it goes down to 0. Okay, so that's the standard convolution operation between two functions in a continuous space, you can say. I mean, of course, this is not like continuous, but still it's better than discrete. Okay, because we're trying to like apply at each possible location. So if you think about this, what's happening when you are trying to convolve a function in a kernel, of course, output is like some kind of response. And if the structure of the kernel matches with the structure of the function, you will get a very high response. Okay, so that's the key. We have like discussed this several times, and it will keep coming. And that's exactly what we're looking for. If you can match the pattern, you will get high response. If you don't match the pattern, you will get a low response. Okay, so that's the whole purpose of performing this convolution operation. And this is like the continuous equation, which we have seen earlier as well. Okay. So this is a one-dimensional, but in convolutional neural networks, usually we use 2D kernels, or you can say like 2D convolutions. So you can just extend these 1D functions to two-dimensional functions. In that case, instead of like looking at patterns which are one-dimensional, you will look at two-dimensional patterns. But the intuition remains the same. You're just trying to do pattern matching. And one example, which I think when we're talking about edge detection, this is a very interesting case of a convolution, you can say. So here the kernel is kind of, you can say it's an edge, because we are going from positive values to like 0 and then towards negative. All right, so this is kind of an edge you are seeing here. And this pattern is actually something which we are trying to find in the input image. And this is something for the edges in the y direction. So even when we're trying to perform Sobel edge filtering using these filters, we were trying to find these patterns in the input image. And if we were able to find this pattern, we get a high response, and that's how we detected those edges. Okay, so in this case, if you think about the convolutional neural network, the structure I showed you, the input image is the, let's say, some kind of volume you have like in your network. In this case, it's like input volume. And these are the kernels. In this case, these are handcrafted. But for CNN, we are going to learn these kernels. Okay, so these are the kernels. And these are the output activation maps, which we are going to stack together to again form a feature volume. So in this case, if we have like two different kernels, we got two different activation maps. We can have several other kernels. We'll get like similar, like the activation maps corresponding to those kernels. And then we can stack together all these activation maps together to be again like fed to another convolution layer in your architecture. So let's try to understand this operation. I will show you like several visuals so that everything is clear and there is no doubt once we are done with this lecture. So let's say this is your input image patch. And in this case, it's a binary image. So one represents like a very, you can say like foreground, and 0 represents background. So in this case, you can see like this is some kind of, in this area, it's highly active. And this is kind of background, right? So in this case, if we try to use a filter like this, if you try to visualize what this filter represents, it's simply a cross, right? So then ideally what should happen is if you use this filter over this input patch, it will give you activation map, which will represent which location you are able to find these crosses in the input image patch. Okay, so if you carefully analyze this, I mean, we don't have any crosses at all, right? We do have partial crosses. For example, you can look here. So this side we have, but if you look at the other axis, I mean, this is kind of half cross, right? If this would have been one, this would have been a perfect match. Then let's see like what will happen if we try to convolve this filter on this input image patch. So you can apply like at this location, again, it's element-wise multiplication. You know how to perform filtering. You just perform element-wise multiplication and add those values. It's going to give you 4, 3, again a 4. You can keep doing that, okay? So now if you try to analyze like what kind of activation map you got, the highest value was 4, right? And you got that value at 3 different locations. So if you try to analyze what the input image patch was at these locations, then it was kind of partially matching with the cross. Not a perfect match, but still it was like some kind of match, okay, even at this location. And the lowest value is 1, which is at this location. And you can see that it's the only match we have is for this location, right? If we try to create a crosshair. And that's why it was like very, it was not highly active. Okay, so let's try to look at it with a more intuitive example. For example, if this is your some kind of activation map, if you try to visualize this, we have like activity in this region, right? And this shape looks something like this. Okay. Now, if this is your input image, the triangle shape, and let's say we are interested in this location. Okay, so it will look something like this. And this is the input image. And if our kernel is something like this, which I showed you earlier, you can see like this actually is matching perfectly with this kind of shape, which means that if we are using this filter to convolve this image, then if you try at this location, you should get like very highly activated values. Okay, so the response should be very, very high. Because on the left, it's like patch from the image. And on the right, that's our kernel. Of course, like they look almost similar. That's kind of deliberative. So if you convolve these two, you can see that it's just element-wise multiplication. For all zeros, you will get zeros. And for all ones, it's a perfect match. So you will get 1. And you can just add those values. It will give you 5, which is like a big positive number, which means that the kernel was actually matching with the input image patch. And in a way which says that, okay, we found this match. Now let's try to apply the same kernel at a different location. And it's the same image, but it's just a different location. Okay, so the input image patch will look something like this. And you can, if you try to just binarize this, you will have these values. You can see like that L kind of shape can be represented using these values. Now, if you convolve this with the kernel we had, which was this shape, then you can perform the convolution operation and you can see that it's just going to give you number 1, which is much smaller than 5, which means that you were not able to find the pattern you were looking for in the image. Okay, so then the idea is, of course, using one filter, we can find that pattern. But the interesting aspect is we don't just use like 1 or 2 filters like we were doing in the case of edge detection. We try multiple filters, and each filter is trying to find a pattern, which is actually the pattern it's carrying itself. All right. So if we have like a set of these filters, then we can actually find all those patterns in the input image. And then depending upon that, that pattern matching, we can say that, okay, if some set of patterns are present, we can actually use that information for inference for any kind of downstream task, whether it's classification or something. So that's in a way is trying to find features in your input images. Okay, so if you think about this, let's say you have these two different filters. So when you're trying to apply this filter in your input image, that's, let's say, if it's going to give you the green activation map. If you try to interpret this, and so this green activation map is actually just telling you at which locations in this input image this pattern was present. Similarly, the orange map here, it's just telling you on which locations in this input image the pattern of the second filter was present. Okay. So let's try to see that using this simple example. And again, this is something we have seen in edge detection. You will have your input image and you will have different set of kernels. In this case, I'm showing you 2 different kernels. The first kernel is, let's see, the red one, which is like a edge slanting towards left. So if we use that filter to convolve to the input image, you can see like you will get the feature map something like this, which is trying to find all the edges which are in this direction. Similarly, the green kernel, you can see that's an edge in the right direction. That's another kernel. Again, that will give you a feature map, which will be highly active in those locations where you have edges which are slantly like leaning towards right. And again, these are just 2 kernels. If you have lot of such kernels, you can find like very interesting patterns in your input image. It can be used for feature extraction.